Have you ever heard of this strange paradox in AI? You build these models bigger and bigger, pour in more data, more compute, and then suddenly they just get dumber? They completely collapse. And the craziest part? It's not some simple bug in the code. The answer, it turns out, is hidden in geometry. So let's really unpack this mystery. Imagine you've just spent, I don't know, millions of dollars and months of your life training a gigantic AI model, one with hundreds of layers. And then, out of nowhere, its performance just takes a nosedive. All its knowledge starts to get muddled, redundant. Basically, it just collapses into a useless mess. So what on earth is actually happening here?
Well, what researchers are finding is that the answer isn't where you'd expect to find it. It's not in the code. It's not in the data. It's not even in the complex math used to train it. The real problem, the root cause, is geometric. It's all about the shape and structure of the information flowing through these massive networks. And to really get it, we have to put on a different hat. We have to stop thinking like programmers and start thinking like, well, geometers.
Okay, so to really see what this geometric problem looks like, we've got to dive into the basic architecture of these deep networks. That brings us to our first section, which we're calling the problem, the highway to nowhere. And trust me, you're about to see exactly why it's earned that name. All right, so the backbone of pretty much every huge AI model out there today is something called a residual connection. The easiest way to think about it is like an information highway. See, at every single layer of the network, the model just takes what it already knows, let's call that old, and adds a little something new, an update. The formula is literally that simple. New equals old plus update. And this idea, it was an absolute game changer. It's what solved the dreaded vanishing gradient problem and let us build these incredibly deep models in the first place. But of course, there's a catch. A big one. This information highway, well, it has no guardrails, no exits. The model can only ever add information, layer after layer after layer. It's a one-way street. And that makes a really dangerous assumption that every single update is a good one. As this highway gets longer and longer, a tiny hidden crisis starts to build up, and it's all about to go wrong. And here it is. This is the geometric problem right in front of you. Think of that green shape as the data manifold. That's just a fancy way of saying it's the space where all the good, sensible information lives. Now, as the model learns, its internal state, the green path, is supposed to stay inside that space. But look what happens. Those updates just keep adding up, and the path starts to wander off right into a realm of pure nonsense. This is what's called off-manifold drift, and it's the first crack in the foundation. So this drift, it has a really devastating consequence called rank collapse. Now, rank here is just a way to measure how rich and diverse the AI's knowledge is. As the model drifts off that manifold, its internal representations become totally redundant and useless. It's like you have a massive library, but every single book starts to say the exact same thing. At that point, it doesn't matter how many more layers you add to the network. You're not adding new knowledge. You're just echoing the same corrupted ideas over and over. The model has officially collapsed. So the big question is, how do you fix a highway to nowhere? Well, the first big breakthrough came from tackling the problem in two parts. First, you've got to keep the cars on the road. And second, you need to give them a way to do more than just drive forward. You need, you guessed it, guardrails and reversible lanes. So these guardrails come from a really clever technique called Manifold-Constrained Hyper-Connections, or mHC for short. All you really need to know is that mHC basically forces every new piece of information to point in a valid direction. It keeps the model on that sensible data manifold we talked about. It's a set of mathematical guardrails that stop the model from just wandering off into that sea of nonsense. So how does it actually build these guardrails? Well, it uses this clever process called the Sinkhorn-Knopp algorithm. Now, don't worry about the name or the math. The main thing to get is that it's an iterative process. It sort of nudges the model's updates in the right direction, step by step, about 20 times for every layer. But, and this is super important for later, the key word here is approximation. It gets really, really close to perfect, but it never quite gets all the way there. Okay, so mHC gives us guardrails. Great, the information is staying on the road. But we still have a huge problem. Our highway is still a one-way street. The model can only ever add information. And this leads to something researchers call residual accumulation. Basically, once a bad or noisy piece of information gets in, it can never be removed. It's just stuck there, getting carried along for the whole ride, gumming up the works and cluttering the model's brain. And the solution to that is something called deep delta learning, or DDL.
And if MHC gave us guardrails, you can think of DDL as giving us reversible lanes. This is a totally new kind of connection. It doesn't just add information. For the first time, it gives the model the power to subtract, to erase, and even to rewrite old information as it goes. In other words, the AI can finally learn how to forget.
And the difference here is just profound, right? Your standard model is just new equals old plus update, simple addition. But with deep delta learning, the whole process gets way more sophisticated. The new formula lets the model write and erase information. That little subtraction sign is everything. It means the model can now learn not just what to add, but also what to get rid of, and even how strongly to make that change.
And the researchers who came up with DDL put it perfectly. They said it enables the network to forget or rewrite features. Think about what a huge shift that is. We're moving away from this idea of just piling on knowledge, layer after layer. Instead, DDL turns it into a process of refining memory over time, which, when you think about it, is a lot closer to how our own brains work. All right, so now we've got two really powerful ideas, but they're separate. We have MHC, the guardrails, controlling the direction of travel, and we have DDL, the reversible lanes, controlling the movement, forward, backward, or even a full stop. So what's the next logical step? You guessed it. Combine them into one super smart highway.
And that combination is called the Manifold-Geometric Transformer, or MGT, and it really is the best of both worlds. You've got the MHC part acting as the guardrails, controlling the direction of every update. It keeps the car on the road. And then you have the DDL part acting as the reversible lanes, controlling the magnitude and sign of the update. It's what lets the car go forward, stop, or even reverse. You get a system that can steer, accelerate, brake, the whole package. Now, you'd think the story ends right there, right? MGT sounds like the perfect solution. But, this is how science works. Even the best solutions often have these little hidden flaws. And it turns out, those original guardrails, they weren't quite as perfect as everyone thought. And that led to a whole new refinement, a much more elegant way to build them.
So here's what was wrong with the original MHC. First, something called the approximation gap. Remember when I said that Sinkhorn-Knopp algorithm uses about 20 steps? Well, 20 is an infinity. It leaves these tiny little errors. And over hundreds of layers, those tiny errors can add up and actually make the whole thing unstable, the very thing the guardrails were supposed to fix. And second, it was just a pain to work with. Making that iterative process run fast required a ton of specialized custom code, which meant it was really hard for other people in the field to actually use it. And the fix for these problems? It didn't come from writing better code or throwing more computers at it. No, it came from a much deeper and honestly more beautiful place, a piece of pure mathematics called the Birkhoff-von Neumann theorem. Now, this is a really powerful idea from linear algebra, and what it says is that you don't have to approximate a perfect guardrail. You can build one directly. You can construct it perfectly, just by cleverly averaging a bunch of simple matrices that just shuffle things around. And this brings us to the final brilliant upgrade, mHC-lite. The difference here is just so cool. The original MHC used approximation with a clunky, iterative algorithm. The result was something that was almost stable, but really complex to implement. mHC-lite, on the other hand, uses exact construction based on a deep mathematical theorem. And the result? A system that is perfectly stable and way simpler to put into code. It's a total win for mathematical elegance over just brute force crunching. And the folks who created mHC-lite captured their whole philosophy in this one amazing line. Exactness, when attainable, is often the most efficient form of approximation. I mean, think about it. Why waste all that time and energy trying to get close to a perfect solution when a little bit of deeper math lets you build it perfectly from the get-go?
So let's just quickly recap this whole journey. We started with this simple one-way highway that was doomed to crash. Then we added some pretty good but ultimately flawed guardrails to keep it on the road and some reversible lanes to let it forget things. And finally, we threw out the flawed guardrails and built perfect ones based on pure math. This whole evolution, it really points to a brand new, maybe more mature way of thinking about how we build powerful AI.
And all of this leaves us with one last big question to chew on. For years, the whole story of AI has just been about scale, right? More data, more computers, bigger and bigger models. But what if this story points to a totally different path forward? What if the future of AI isn't just about building bigger, but about building smarter? What if it's about digging deep and finding these elegant mathematical principles to create models that are not just insanely powerful, but also stable, efficient, and built on a foundation that won't just suddenly collapse?